So with regard to the four classes of reactions that we're going to consider in this class, I have saved the most important for last. And that is the double displacement reaction, which is also sometimes known as the exchange reaction or the metathesis reaction. You're going to see all three of these terms. I'm probably going to use exchange the most just because it's the shortest. So our example of an exchange reaction from lesson 3 was when you had an aqueous solution of sodium chloride reacting with an aqueous solution of silver nitrate. Okay, so that's where we dropped silver nitrate out of a dropper into a beaker containing sodium chloride. And the products of that were an aqueous solution of sodium nitrate and solid silver chloride precipitated out. Okay, so when you want to classify a reaction as a double displacement reaction, there are several things that you want to look for. So the first thing you want to look for is that the reactants switch partners to form the products. Okay, so initially the sodium is partnered with the chlorine and the silver is partnered with the nitrate. They swap partners, right? Because in the product, the sodium is now partnered with the nitrate and the silver is now paired with the chloride. The second thing you want to look for a exchange reaction is that the reactants, first of all, there are going to be two reactants, but the reactants are both ionized in aqueous solution. Okay, so anytime you see an AQ next to something, you could assume that it's ionized, but you're also eventually going to have to figure out that sodium chloride and silver nitrate are actually both soluble, and as a result, they're going to be ionized in solution. You could have an ionic compound, or you can actually have an acid, which also ionizes in solution. So notice I said that the reactants are both ionized in solution, not that they are both ionic compounds to start with. Okay, and then finally, when we're looking at the products, one of the products is usually going to be a solid, therefore it would be called a precipitation reaction, a gas, in which case it would be called a gas-forming reaction, or liquid water, which is actually one of the products of an acid-base reaction. Gas-forming reactions don't have to be double displacement. They can actually be several classifications of reactions, but precipitation reactions and acid-base reactions are two of the important examples of double displacement reactions that we're going to look at. Okay, so now I want to turn our attention to another example, and that is the reaction of lead nitrate with potassium iodide to give lead iodide solid and potassium nitrate. Probably going to be doing this in the lab. This is a very, very common lab experiment in general chemistry, but just for the moment you can see what happens. So in the dropper, in the pipette here, you can see that there is a colorless solution of lead nitrate. In the beaker, there is a colorless solution of potassium iodide, and as the lead nitrate is dropped into the beaker, we form a bright yellow solid, okay, and that is the lead iodide, and then of course the potassium nitrate stays in the beaker, and it is clear, colorless, and soluble, so we write an AQ next to it. Okay, so that's the picture of what's happening macroscopically that we can see with our eyes. Now we have to ask the question is, what is happening in solution during this reaction? Okay, so what I want to do is first look at the reactants. Okay, so potassium iodide means that there are K+ ions and I- ions dissolved in the water. Okay, so that's what's in our beaker of water. And from the formula Ki, there are the same number of each type of ion. So in this picture of the cartoon of the beaker, I have drawn 2 K+ and 2 I-. That will actually become important in a minute why I chose 2. So then lead nitrate aqueous means that there are lead 2+ ions. Okay, so to be able to solve these problems, you actually have to know that lead forms a +2 ion. And then there are also nitrate ions dissolved in the water. Okay, now, so remember that nitrate is a polyatomic ion, and that polyatomic ions do not break apart further in solution. Okay, so those NO3s have to stay together. You're not going to take off an oxygen or a nitrogen or anything. And then from the chemical formula, PbNO3, there have to be twice as many nitrate ions as lead ions. So in this beaker, I have drawn one lead 2 plus and 2 nitrates. You can also look at this based on balancing charge. There's 2 positive charges on the lead, so there have to be 2 negative charges on the nitrates, and that, of course, is going to be true because a nitrate ion has a 1 minus charge. Okay, now it should be clear to you why you needed to learn all your polyatomic ions and their charges. Okay, and then finally, from the balanced chemical equation, which is up at the top of the screen, lead nitrate plus 2 Ki, that tells you there needs to be twice as many potassium ions and twice as many iodide ions as there are lead 2 plus ions. And this should also make sense. That's why I included 2 potassiums and 2 iodides in that beaker. And this should also make sense that there should be a 2 there, because we have to have 2 iodides in order to be able to form PbI2 as the product. Okay, now let's look at the products. Okay, so KNO3 aqueous means that there are potassium ions and nitrate ions dissolved in the water. Okay, so you can see all of those in the beaker, ionized and moving around. But then PbI2 solid means that this compound solid is not in solution and it is precipitated. So we have that in the cartoon drawn at the bottom of the beaker. And that in fact, to make a solid, ionic bonds have formed between the lead 2 plus ions and the I minus ions in order to form the crystal lattice. And of course, the fact that it's yellow is also indicated in this beaker. Okay, and then again, from the balanced chemical equation, there are twice as many K plus and NO3 ions as there are PbI2s, and this is reflected in the diagram. We've got 2 K pluses, 2 NO3 minuses, and just 1 PbI2. Okay, so what I want to do at this point is introduce you to the topic of ionic equations. So what I had written on the previous slide, PbNO3 2 aqueous plus 2 Ki aqueous giving PbI2 solid plus 2 KNO3 aqueous, is what we as chemists call a molecular equation, because those formulas represent the actual chemicals that you would put into your beaker. Okay, so here is drawn a bottle of lead nitrate and a bottle of potassium iodide. You literally take these chemicals as salts and dissolve them up in water. But then, once you dissolve it up in water, each of these compounds ionizes. So the ionic equation shows each ionic compound dissociated into the ions that will actually exist in solution. So the ionic equation for this reaction would be Pb2 plus aqueous plus 2 NO3 minus aqueous plus 2K plus aqueous plus 2I minus aqueous. Okay, so we've taken each of our starting materials, separated into ions, so now we have 4 different ions in solution, and then our products are still PbI2 solid. Okay, so if you have something that's not aqueous, that's a solid, it's going to look exactly the same as it does in the molecular formula, plus 2K plus aqueous plus 2 NO3 minus aqueous. Okay, so how did I do this? Well, I'm going to give you 7 rules to remember when writing ionic equations. So the first is make sure each soluble compound is dissociated into ions. Okay, so whenever you have an ionic compound, something that has an aqueous next to it, you're dissociating it into cations and anions. Okay, so you have to put the appropriate charges on each ion. The cations are going to have positive charges, but you have to remember some cations are +2, some are +3, etc. The anions are going to have minus charges. These are, in this particular example, the anion is -1, but there are also going to be -2 and -3 anions. And then you want to write aqueous after each cation and after each anion. Okay, so in going from the molecular equation to the ionic equation, we have gone from 3 AQs in parentheses up to 6 AQs in parentheses. Okay, so then if there is a subscript on an ion in the molecular formula, okay, so the subscript of 2 for lead nitrate, you need to put a coefficient in front of the ion in the ionic equation. Okay, so that's why we took that 2 from that was a subscript and now put it in front of the N of nitrate. If there is a coefficient in front of a compound in the molecular equation, such as the 2 in front of Ki, you want to make sure that coefficient goes in front of both of the ions in the ionic equation. So that's why there's 2 K pluses and 2 I minuses. You have to make sure you don't break apart chemicals that are not soluble. Okay, so as I said, lead iodide solid is exactly the same as it is in the molecular formula. And finally, the rule once again, I know I sound like a broken record, but do not break up polyatomic ions. The N and its 3 oxygens in the nitrates have to stay together forever. Okay, so those are ionic equations. I'm going to take a break now and call this lesson done, even though I have one more topic to talk about. That topic I will pick up in the next lesson, and that's what happens when we get into the topic of spectator ions, and that will lead us into net ionic equations.